Okay, so let us continue. Um, so what we had, let's see here, we had gone through the first part of the proof of theorem 652. So they had instructions for using the eraser. Okay. So B and C, I kind of skipped over because it's, well, actually, I did outline it a little bit, but it's pretty straightforward. C implies D. Suppose in this case that what we have is F isomorphic to a direct sum of Ri, with each Ri is isomorphic to R via the homomorphism phi sub I from Ri to R. So, and of course, these are all cyclic, singly generated, or cyclic R modules. So for all I, this is kind of as it left off, we have this community diagram. This is phi I. Let's see. Well, no, I'll just do this. Yeah. RJ. J in our index set. Oh, and this would be now, what we're trying to do is we're trying to establish this part B of the theorem. That is to say that there is a set that has this universal mapping property. That is, there's a set X and a map from X into F, such that any map of functions from X into another module M induces an R module homomorphism from that direct sum into M. So we're going to define X thusly set X I such that let's see, B I of Xi. And remember this phi, so basically what Xi is, so Xi goes to 1 here. No, 1 is the generator of R as an R module. And so really all I'm doing is I'm cherry picking out the generators of Ri. That's essentially what I'm doing. This is an isomorphism here. 1 is the generator here, the pre-image, what I'm calling Xi, is the generator of Ri. So I'm just cherry picking out. And this is what I am going to make to be my set X in the statement of part D. And so we're going to define, now I need my function, iota from X into F. And the way it's going to work is iota so my input is an element of the set. Where does it go? Well, take that Xi and just see where it goes here in the direct sum. And so my input is an element of X, my output is something in this direct sum. And and let F be any function you want from X into M. And so with this function here, we'll say that F of Xi equals Mi, right? Because this is our set of elements of Ri. F of Xi goes to Mi because some function takes it here. That's really a notational thing. And the desired homomorphism F bar from direct sum Ri into M is given by F of the sum over well, I and I, all right. Over Xi is equal to sum of Ri and don't let this bother you too much because, of course, the first little alarm bell that might go off is, oh my goodness, that index set may be very, very big. But remember, again, this input is an element of the direct sum, which means these Ri's are zero almost everywhere, which means this is a finite sum. And so this output is a finite sum and everything's hunky-dory. You should have actually sort of verified also that this is well defined in your last homework, because remember, we actually went through that business with the function from the direct sum into R being well defined, because in the direct sum, we have a unique representation of this form. Okay. Any questions on that? I'm going to leave D for the implication D to A as an exercise. But so think of X there as your basis and see if you can well, think of how to take that that set X that they give you in part D and getting a basis out of it. And I think it's fairly straightforward to see. Okay, any questions? Now, when I first talked about direct sums, so direct sums are, of course, more general. What we should get from this theorem is, when I say a free module, one of the equivalent conditions of this theorem is a free module. So if you have a free module over the ring R, that's merely a direct sum of some number of copies of R, right? And I did sort of try to sell you that direct sums were very, very important because they are the parent of all the R modules. And so let me kind of put my money where my mouth is on that one. This is the importance of the free modules, and it's the importance of direct sum here. Every unitary module M, so implicitly we're over a ring of identity, is the homomorphic image of the free module. Additionally, if M is finitely generated, then M is the homomorphic image of a finitely generated I'm going to prove this for you. It's kind of cool. So in other words, so for example, so let me kind of restate this. If R is R, if M is an R mod, then there exists an onto homomorphism F onto M, where F is free. So any module is the homomorphic image of a free module. And another way to think about that, if you like thinking about quotients, is M is isomorphic to F mod the submodule kernel phi. So any, if you're over a ring with identity, any R module that you can come up with that's unitary, any of them, is some free module, module of the kernel phi. And not only that, if it turns out that M is finitely generated, you can select F to be finitely generated. Be careful about this wording here. If M is finitely generated, it doesn't mean that F has to be finitely generated. It means you can pick F to be finitely generated. Right? So let's prove this. This corollary by itself is just too sexy. So let's show this here. So let X be a generating set. Right. Now, let me point out, I think I pointed out the at this conversation with somebody after class today. I hope this is too obvious for me to say it, but it probably is. So it's natural to say, do you have a generating set for a module? And the answer is, of course you do. In fact, if you wanted to be really, really inefficient about it, you could take X to be all of M, right? Because everything in M is generated by stuff in M, right? But of course, usually one would expect that X is sort of tighter or compact. But anyway, so such a thing does exist. So we don't have to worry about that. So let X be a generating set for M. And let me kind of draw a diagram here. Let F be free on X. And what I mean here is, let me be clear about what I mean by free on X. X is a subset of M, so it may have some relations on it, right? Like X1 plus X1 might be X2 or something like that. When I say free on X, what I mean is you just take these symbols just as an abstract set and make the free module on that with that basis. So it has no, there are no relations. So for example, a typical element of F would be the sum, well, a typical element would be R1, X1, plus RK X for some K choices of X in this set. Now, as an element of M, these may have relations on them. So this might add up to 0, right? But when I say free on X, I mean, forget about all those relations and just take this to be an abstract set. And so these X's out now act as a basis, right? So I'm gonna let F be free on X. So here's my inclusion for this abstract set I've got here. And here's M. And I've got, well, I'm going to call this inclusion into F and inclusion into M, right? So because we have this diagram here, let's see. Well, they will both of much here. All right. Then, because of the fact that F is a free module, there exists F bar from F to M such that when I do, well, I better specify that. When I do inclusion F, then F bar, this is inclusion in M. Everybody okay so far? So this is an honest to goodness homomorphism. So there's my homomorphism from F to M as promised. Now, I did say it was going to be onto, so I better prove that. That any generator X in X. So notice that if I have an arbitrary generator X in X, then I to F bar X, right, by the commutativity of this diagram. X goes out F bar, it goes to X. Right. This means, so every generator of M is contained in the image of F bar. Because I can hit every generator of F by plugging in something from F and it goes to that generator. So M must be contained in the image of F bar. Because every generator of F, every generator of M is in the image of F bar. And the other inclusion, that is, that's always the case, right? Because it's homomorphism, the image is always contained in this. Therefore, image of F bar equal M, and so F bar is on. Okay. Any questions on that? Any questions? Yes.
Right, like every generator, generator X, like, but we say that X is a generating set, so should we call the element of the generating set a generator? Like for that, I kind of hear that the X will generate all of M. If I will say that something is a generator, so I'm a bit confused about why you call X a generator.
When I call this, note that I don't know why there's an and there.
Do you want to say an A?
Yeah, I don't know. I was talking too fast here. Such an FI is. Note that any generator is in M, right? So X is the collection of all generators, right? This is the set that generates. So everything in M is a finite linear combination of stuff in X. And what we show here is any generator, any element of this set is in the image of F, right? So that means that everything in M, so if you have something in M, it's a finite linear combination of some things that are in the image of F. And so M is contained in here, right? Did I answer your question?
I got the stuff, but I just didn't get like the calling of the element of, like, why do we call the element of X a generator? Like,
Oh, okay.
that's
I think if I'm interpreting your question right, when I say that, I don't mean that the little X generates everything.
okay,
What
yeah,
I mean is it is a particular element of this set of generators, right? So,
Okay.
for example, let me give you something concrete. would everybody agree that these two elements generate Z sub Z, right? Because every A comma B is A times this, right? This thing of two elements is my generating set, and I'm calling these little elements a generator, even though that I only call that because of their membership in the set. That doesn't mean that the individual element generates the whole set. You gotta have all of them, right? Okay, any other questions? Okay, so this one, I sort of think of this corollary here as kind of a giant theorem. Very important because any R module is a homomorphic image of a free R module. And with that, I am now going to turn my attention. I'm going to actually specialize a little bit, and I'm going to rip off some stuff about vector spaces, which y'all probably seen from the past. But first question, how many of you all, did Matt ever do anything with Zorn's lemma last minute? So he proved, I'm willing to bet a community bring with identity has maximum ideal. If I use Zorn's lemma there. Okay, so maybe I'll do kind of a quick thing about it. So let me start with kind of my specialization here. Let me say a maximal, let V be a vector space. And remember, all I mean by vector space is this is an R module over a division ring, right? If I want to be non-commutative, or if you like to be exclusively commutative, which I usually like to be, this is an R module over field, right? But it'll be easy to do the division ring case here. A maximal linearly independent subset of the vector space V over a division ring D is a basis. A maximal linearly independent subset of V is a basis for V. Objection, Your Honor, fact's not in evidence, right? That's what you probably should say. And the fact not in evidence is, how do you know that there is such a thing? I'm not claiming that yet. I'm going to prove that there is a maximal linearly independent subset. But for right now, give me a little latitude, Your Honor, to move ahead. Suppose that we actually do have a maximal linearly independent subset. I want to show it's actually a basis. So we'll just suppose that such an animal exists for now. Okay, proof. Let X, and let's say it's not going to be a maximal linearly independent subset of V. We're supposing this thing exists. Let me point out, I tossed out the empty set case, but if it is the empty set, you can actually prove that the vector space must be zero. Now, what do we need? We need to show that this X is a basis for V, right? What do we need for a basis? We need it to be linearly independent. Well, ding, 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 ding. And we need it to span. Now, that's the part I don't know. So note, V is linearly independent, but does it span? That's the question at hand. We got to figure out. So in this, so So let W be the subspace of V that's spanned by X. Notice that, of course, X is a basis for W because it's linearly independent. It spans W by definition. Right? If W equals V, we're done. We can go to the house, right? No problem. What not, or what if not? If not, then there exists a V in V, not in W. All right, so we can pick something out. So our strategy is we will prove so this is our strategy. We're going to prove that this new thing, union the original X, is linearly independent, and that will contradict maximality of X. Everybody cool with it? Okay, so to this end, suppose we can find, and there's actually, I want you to pay attention because there's something really kind of cool here that happens. We can find, let's see, where was I? D and D1, D2, Dn in our division room D. And let's say X1, X2, Xn in X, such that dB plus D1 X1 plus D2 X2 plus Dn Xn is equal to 0. Now, of course, as you might guess, my goal here is to try to show that all those D's are 0, the D's and the subscript, right? How might I try to go about skinning this cat?
D is equals to something, but then the other inverse.
I hate writing minuses, so I will take your advice and do it this way. So I've certainly got this here, right? Now notice that D is not, if D is 0, then if D is 0, then that equation turns into that. And so, and this implies that D1 this implies the rest of them are 0 because X was a linearly independent set, right? And so this equation right here gets at all the DI's. Everybody okay with it? Now, if D is not 0, then because it's a division ring, you can invert it, right? Then equals minus D inverse D1X minus D inverse D2X minus D inverse Dn Xn X1 X2. There we go. What's the problem with that?
That's the W.
That is correct. And this is a contradiction. Now, let me point out the absolute importance of this right here. It seems like not a big deal, dividing out by that D, but when you talk about rings, this is huge. So let me give you kind of a, so let me finish this thought. So, have the union X is linearly independent, and this is a contradiction. So, so X is a basis for let me point out this little step right here in the proof is really kind of central because, for example, Z is a free Z module, right? A free module over a division ring is called a vector space, but this is an ordinary free module over a ring that's not a division ring. Notice that 3 is a maximal linearly independent subset. That's it. Right, because we already did an example earlier that if you take 3 and you add any other integer to it, then all of a sudden you have a linearly dependent set. So this is a maximal linearly independent set, but it's not a basis because it doesn't. If you look at the span of this, it's only multiples of 3, so you're missing essentially 2/3 of the integers. Right? So this is a key sort of difference of what happens when you sacrifice division rings here. So let me kind of finish my idea here. And of course, this kind of subtle problem is going to free Z modules are super cool. Every R module is a homomorphic image of them, but there are some limitations here, right? Linear algebra, the fact that things are a field allows you to do a little bit more. But let me give you this theorem, 656 as promised. Every vector space V over a division ring V has a basis. And so it's free. And in fact, I'm going to take this a step further. So I'm going to make a statement that's slightly stronger than this. In fact, every linearly independent subset of a vector space can be expanded to a basis. Okay. So here's one thing that's not limited from linear algebra to module theory, and that's this old chestnut here. If I walk up to you on the street and I give you a linearly independent subset of a vector space, you can start cherry picking and putting other elements in to make it a maximal linearly independent set. So you can expand anything to a basis. So start with any linearly independent set. You can sprinkle some fertilizer and water on it and grow it to a basis. So this is where This is where I've got to use. Actually, you have to use Zorn's limit. You have to use the action of choice here. So stop me if I go too fast with some of the detail. We can kind of rework our way through this. Proof. If b equals 0, then our basis is the empty set. So we're gonna let me just start that case, right? If you have an empty basis, that means you have no linearly independent subset over a division ring. That means that basically your vector space is 0. So we'll assume from here out that B is not 0. Let's just make it interesting. Right. So let X be, well, let me also make one other remark. Let 0 into P be a vector space. And then V by itself, as long as V is not the 0 vector, is a linearly independent subset, right? Let me prove that for you. So suppose that DB is equal to 0. Multiply both sides on the left by D inverse. Right. And that's a contradiction because we chose V not be 0. So if you have any singleton vector that is not 0, then you have a linearly independent set. And the reason I point this out is now let X be a non-empty linearly independent subset of them. By this remark, such an animal has to exist, because all you have to do is take a single non-zero vector, right? So we don't have to worry about the existence of this, they're out there. Now, we're trying to prove we have a basis. In fact, we're trying to prove something stronger, that is that X is contained in the basis. So let's call this crazy Greek letter gamma. Let gamma be the set of Y and W, or I'm sorry, Y and B. I'm looking at all subsets of B that have two properties. Number one, Y contains X, and two, Y is linearly independent. So this crazy gamma is the collection of all subsets of my vector space B that contain X and are linearly independent. This is the set that I am going to do Zorn's lemma on. Remember, what Zorn's lemma says is that if you have a partially ordered set such that any chain in the set has an upper bound, then that set has a maximal element. Right now, here's my set. It's just all linearly independent sets of X. There's a couple things that we probably need to make sure of first. Number one, how is it partially ordered? What do I mean by that? Right, it just behaves well under the what is our partial order? Inclusion, right? So if I take Y1 and Y2, these are two linearly independent sets that contain X, then it may be the case that Y1 is contained in Y2, or it may be the case that Y2 is contained in Y1, or it may be the case they're not comparable, right? Like X might consist of AB and Y might be ABD, and Y2 might be ABC, one of them might be ABD. They might not be comparable, but when they are, they satisfy the axiom of being partially ordered. right? Anti-symmetry and so forth. Everybody okay with that?
Yeah.
Okay, here's another big one. Is gamma the empty set? Right, I don't want to prove a bunch of crap about the empty set, that's a little embarrassing, right? No, gamma is not empty. As X is in gamma. Because X is a linearly independent set and it contains a set. Now, I think that we've kind of got the preliminaries out of the way. What we need to do is show that every chain has enough bound. So let C, let's see, Y alpha is an index set, be a chain in gamma. Now, what does it mean to be a chain? Does anybody remember?
You can't put the order.
Correct. So a partially ordered set is like a big barrel of apples and oranges, right? Some of them you can compare, some of them you can't. A chain is all apples, right? You can always compare. So when I say a chain, I mean a totally ordered subset. So if I pull two of these out at random, say Y alpha and Y beta, one of them contains the other, right? Okay with that? Now, we have to show that every chain has an upper bound, right? How can we show that? Well, let me ask you this. Here's a more pointed question. What should the upper bound of our chain be?
Yeah.
So let's let U be the union of all those. Right, so I just take, remember, this is a chain, so it's a sort of, everything's in all of it. Yes.
Should that be indexed by the natural numbers if it's a chain?
No, chains can be arbitrarily large. You can index by
Uncountable, it can be uncountable.
it can absolutely be uncountable. What it means to be a chain in general is if you have two indices, Y alpha and Y beta, right? Just pull them out there and look at them. Any two are comparable. Either Y alpha is contained in Y beta or the other way around. Yeah, chains can be arbitrarily large. So let's see, what do we got to do here? Well, we got to do, what do we get? Well, certainly U is an upper bound for the chain C if it is in gamma, right? It's certainly an upper bound in the following sense. Any element of that chain is contained in U under this partial order, right? Any element of the chain, because it's a union, every element of the chain is contained in U. And so it's an upper bound as long as it's still contained in gamma. Because remember, the caveat is the upper bound has to be contained in gamma. So I got to check you out. I say, hey, you, are you still a member of this club? Well, what does you have to satisfy to be a member of this club? It has to be a subset of V. No problem there, right? It has to contain X. No problem there, because every Y alpha does, so certainly the union does. Here's the rub. Does it have to be linearly independent? So you need to show U is linearly independent. How are we going to do that? How are we going to do that? Okay, yeah, let's suppose not. Then there exists U1, U2, up to UK in U, such that D1 U1 plus D2 U2 plus DK UK is equal to 0, and each DI. In fact, you can assume every one of these DIs is non-zero, because if any one of the D2 was 0, then I'd just throw U2 out and I'd have a shorter representation. Everybody okay with that? So if it's not linearly independent, I should be able to cherry pick elements of U and elements of the DI such that I get a non-trivial way to write 0. And there's a problem with that.
Basically, there has to be a set that contains all of those.
That's exactly correct. So where do these U's come from? Well, they come from U, which is a union of these Y. So let's say that U1 is in Y alpha 1, U2 is in Y alpha 2, and UN is in Y alpha N. Right? Because they all have to live in one of these here. And without loss of generality, say Y alpha 1 contains all other Y alpha i's. This is the totally ordered part, right? Because, for example, if you look at Y alpha 1 and Y alpha 2, one of these contains the other one. We'll say this one wins the contest. Now compare Y alpha 2 to Y alpha 3. We'll say that this one wins the contest and so forth, right? So there's one of these that contains all the rest. Hence, U1, U2, up to UN are all in Y alpha 1. And this is a contradiction, as Y alpha 1 is a linearly independent set. So what we've shown is, so U is upper bound of chain gamma. So apply Zorn's lemma. To find B, what's it, has maximal linearly independent subset, which is really group. Hence, a basic. By the previous result. And not only that, we showed that an arbitrary linearly independent set X starts as a seed, can be expanded to a basis. So that's a powerful theorem right there. Okay. Any questions? Let me leave you with one last remark. Then F is isomorphic to the direction of R. Right? So if you have a ring with identity, for example, or a commutative ring with identity, then this is a free R module, right? And any free R module is direct some number of copies of R. That means really to understand this free module, all you need to know is the size of this, right? So for example, if the size of the index set is 1, then this is just one copy of R. If the size of the index set is 2, it's 2 copies and so forth. So on. That was a big theorem for linear algebra, right? That Rn and Rm are isomorphic if and only if N and M are the same, right? However, they're due deep in the depths of some Stephen King novel. If you have any free module over a commutative ring with identity, then any two bases of that free module have the same size, same cardinality, right? You get your cardinality. we will say that a ring has the invariant dimension property if any free module has a well-defined number of elements in the basis, right? However, I've given you a homework problem. If you have F is isomorphic to the correct length K, I think this is accountable any one infinity. This here is a very big ring here. And R if F were a finite number of copies of that field, this would be a matrix ring. However, I've got countably many, and so these are all the R homomorphisms from F to F. For any n, R is isomorphic to the direct sum of R, which is really, really weird, right? So in other words, R as a module over itself has a basis of one element, but it also has another basis of two elements and three elements and so forth. So this actually does not have the invariant dimension problem. But don't worry, most of the rings we look at are right. In fact, any ring that has a division ring is a homomorphic image. So in particular, any ring of identity has this property. Any question? Yes.
I want to talk about the basis previously. It is not necessarily finite, right?
What that?
When you talk about the basis previously, it is not necessarily.
Right. A basis is not necessarily finite. It certainly could be very large.
But now my question is why? Because looking at those two, which it seems like if you take any sequences of vector space, or say, I cannot really say vector space, but it's over a division thing. So it seems like a module over a divisor ring is not there, but it is not.
It seems like what now?
It seems like a module over a divisor ring is not there, but it is not. It should be finitely generated. Not there.
A module over a division ring. Now make sure I'm answering the question correctly. It's a vector space. Right?
What I mean is, it is a notarial module. Because it seems like from that, for every let's say sub module of it, we can extend it and then.
Oh, right. So for example, I mean, even we can take something even easier. Just take the real numbers, right? Take the vector space of continuous functions. Right, the continuous function is a very large vector space over real numbers, and that goes up forever, right? I mean, so you know, you have R inside R squared inside R cubed. You can make that go on forever, right? Because in fact, continuous functions over the reals, I think, certainly has uncountable. It has an uncountable basis. The reals over the rationals has an uncountable basis. Right.